This could be our last video on TLC, so you better take lots of notes and get ready for upcoming tests and assignments on the TLC world because you know what's going to happen. So this last video is going to concern something that we call densiometry. And this is a way that we can basically put quantitative aspects on a TLC plate. Okay? So basically what has to happen in this process is that we have a TLC plate. That TLC plate has been spotted and it's been developed. And we get a spot that happens here. And this is for my sample. Well, like a lot of the other equipment that we've used in the lab, we will make a series of TLC plates. And each one of those TLC plates will have an origin line. And each one of those TLC plates will be spotted by a standard. And I'm going to call this STD1, STD2. You get the picture. Number 3, number 4, and number 5. And what will happen is that all of these plates will develop at the same time. And they're all the same standard, so they'll go up to the same distance every single time. And if my sample goes up to the same distance, then I can say, yes, my standard is present, so therefore I at least know that that component is present in my mixture. Then what would happen is that I would take these standards and I would basically put them onto a machine. And the machine will scan these spots. And if I go up in concentration and I use some type of indicator on those spots, then my spots will become darker. This is the same concept that happens in UV spectroscopy, and it actually works most of the time with a UV lamp. Believe it or not, that's what we use. So we're blending chromatography in with spectroscopy and wrapping it into one concept. All right, well, it knows the intensity from each one of these, and what it can do is it can plot a calibration curve, just like we did in the field of spectroscopy. And once we have the calibration curve, it will then scan the sample. And it knows that this is what I'm looking for because I've told it. And it will give me basically an intensity. How dark is that spot? Almost like an absorbance in spectroscopy. And it will pop out a number that's assigned to that. And that number gets plopped into the calibration curve, and then I can go through and I can solve for the concentration of that unknown. So that's basically how we do this kind of thing. And it doesn't get any more complicated than that. The problem here is that this is not heavily done because chromatography actually takes care of this aspect a little bit better. So if I do have to do quantitative measurements, I would prefer just to go ahead and run a full-blown ion chromatograph or a high-performance liquid chromatograph or a gas chromatograph. I would just get one of those instead. TLC is more for preparatory work. And that's why we don't really see a lot of 2D stuff. And that's why we don't really see a lot of the densiometry that can come along with the 2D TLC plates. There's just better scenarios and better pieces of equipment to actually get this thing taken care of. All right? So that's one of the few topics that we have to talk about last. The second is going to be the development. So I put this TLC plate into a chamber and I'm allowing it to develop. So my spot is getting moved up the plate. What you will see in the very beginning is it will go very quick. Okay? This plate will suck up the mobile phase very, very fast. And the bottom part of this TLC plate will get wet and moist very, very fast. The issue, though, is that the longer it goes, the slower it goes. So the speed of migration is not constant. So let me write that down into a phrase. The speed of migration is not constant. That is a statement that basically says that in the beginning, my spot will go through the roof and it will go up this plate. However, the longer the plate stays in, the slower the mobile phase travels up the plate. And that means the slower the spot travels up the plate. That's just a phenomenon that we see in TLC in general, right? So if I'm using these TLC plates in the laboratory, very tall plates will mean very long times to develop. The taller the plates are, the more time is required to get to the top of that plate. So it's better for me to choose shorter plates instead. That's just a phenomenon that we see in TLC. The reasoning behind it is contributed to 4 or 5 different things. Gravity can actually be one of them. And we don't really talk about it any more than that. So it's just something that we go into the process knowing that if we have really tall plates, if we have very large plates, you're going to be there for a while. And in the beginning, it's going to suck up things very quickly, no matter what size plate that you have. But the further it goes up the plate, the further it gets away from the mobile phase, the further it gets away from that solvent, the longer it's going to take to continue to move. Okay? So we've got a graph on migration rate. And this is what it looks like. So here at 0 time, and then we've developed this plate for 16 minutes, and we look at the migration distance. How far has it traveled? And as you can see, like we said before, it is not a linear curve. So in the beginning, you'll see this graph zoom up, and that's what you see here. And then slower and slower and slower as the time goes on. So it says curve A was obtained in a chamber that was unsaturated with vapor, and curve B was obtained by saturating the chamber with the eluent vapor. And as you notice, B is much higher than A. So that means that the spots in the B moved further. That's the migration distance over here on the y-axis. So that's what we said many slides ago and many videos ago, that if you're developing a TLC plate, you want to put a lid on it. And you want to make sure that the mobile phase vapor gets filled up in that chamber before you put your TLC plate in it. Because not only does it give you a better separation, but according to this graph, it also shortens the time development. You don't have to wait longer for those plates to develop versus somebody that did not fill their chamber full of the eluent vapor before they started. So keep that in mind when you actually do the TLC plate development in the laboratory itself, and make sure that you put that lid on it. And now you know why. Another slide that I want to show you is this one. And this is just kind of symbolic of a traditional kind of TLC plate and what happens as we change the stationary phase and the mobile phases up. So what you're seeing here in the graph up here at the very top, this is called normal phase and this is called reverse phase. So if you look with this one, the mobile phase that they're using is a hexane acetone mix, and it's 80-20. So that means there's more hexane here, more nonpolar stuff. In the second graph, what they've done is that they've flipped it and they've put acetone and water now in a 60-40 ratio. Acetone and water is very polar, and we call that reverse phase in the TLC world. So the first graph is representative of a non-polar mobile phase. And then down here at the bottom, we've got 4 lipids. And these lipids are actually steroids. And here we have methyl testosterone, and then we have two others, and all of them are very similar with a few differences. In the first one, we see a double bond O, a double bond. Well, that's also present in the second one, and that's also present in the third one. So all three structures are the same there. The Me stands for methyl group, so a CH3 compound. We see one there and one there and one there, so there's no difference there. In the third compound, we see an OH group pointed off here. And in this OH group, we do not see it there and we do not see it there. So this has maybe some extra polarity that's associated with that part of the molecule. Then finally, up on the top piece, we see methyl groups with one OH, but we see that same OH there and we see that same OH there. So that doesn't really matter. It's not playing a difference here. So this is just all nonpolar. There's nothing special about this molecule at all. All the OH groups, the double bonds, the double bond O's, these are present in all three compounds that we're looking at. So nothing special here. This one's different because of the OH group that's right there. And this one's different because we see a C double bond O with a CH2OH at the top. But this one's got it as well. So out of the three compounds that I'm looking at, this one's the most nonpolar. Then this one increases the polarity a little bit because it's entering in this double bond O up here at the very top that my first one did not have. And then in the third one, well, this piece is identical to the middle. The difference here is that this is added on an OH group off to the side, which means that this is more nonpolar than the middle one. So hydrocortisone is going to be the compound out of the three that's the most polar. Well, if I look at the graph, it looks like that one's represented as a circle, this one's a square, and this one's a triangle. And if I come up here to the left and I look at how they've migrated, these are the RF factors, right? And we said that lower RF factors are lower on the plate. Well, because this one's the most polar, this one hangs out with the stationary phase the most. So it shouldn't surprise you that on this graph, the circle one is right down here at the bottom, closest to 0. The middle one moved up a little bit further, and the first one goes up the furthest, and that was because that's the most nonpolar. Hopefully that makes sense to you, because you'll see a problem like this maybe on an assignment or maybe on a test. Look at these three compounds. Which one's the most polar? That's the one that will stay behind the most. And the most nonpolar one in this case, this methyl testosterone, would actually prefer the mobile phase because it's mainly nonpolar with the hexane, and that moves further up the plate for that reason. Now down here at the very bottom, what they've done is that they've changed the stationary phases on you. So here they started with silica, and then they switched it to an amine, an NH2 group. Then they switched it to a cyanide or a nitrile group. Then they changed it to a reverse phase 2, reverse phase 8, reverse phase 18. Those numbers represent the number of carbons. But look at the order. The order of them does not change. No matter what I do with the stationary phase in this case, the mobile phase is the most nonpolar, and the most nonpolar piece stays with it. So in this scenario, the mobile phase trumps the stationary phase. The order of elution is the exact same. The difference is how far up the plate do they go. Because if I go more nonpolar on the stationary phase, then this polar compound has no reason to stay behind, right? If it's got no reason to stay behind and lag, then it's going to move further up the plate than if it was a silica-based plate. But the order of elution is exactly the same. The same thing's going to happen over here to the right, and this is they flip the mobile phase on you. This mobile phase is now polar. So if we look at the silica piece in this case, in this scenario, the silica is polar, the mobile phase is polar, and I told you that that's traditionally not a very good setup, right? And if we look, there's no separation. Everything moves up to the top. No big deal at all. Everything is just flushed through. If I change that to an NH2 group, the same thing happens. If I change that to a nitrile group, then finally we get separation of our three components. Well, I can then make this stationary phase more nonpolar. And as I do that, my separation becomes cleaner and cleaner and cleaner. So it's very evident that the best setup here is my nonpolar stationary phase and my polar mobile phase, right? Because that's where those three components have separated the most. Now, that doesn't work every single time. Just in this case, in this particular graph, this hits home the whole concept of making sure that your stationary phase and your polar phase are completely different, or your stationary and your mobile phase are completely different in polarity. And this shows you why. Out of the two graphs, we don't really like the spots that are down here to the bottom. That's a little bit low for us, so this would not be a good setup. The same thing's going to happen here in this nitrile setup. Yeah, they separate, but a lot of these are higher than maybe what's needed, and that would not be a preferred setup either. What we like to see are retention times that are above 0.2 at least and below 0.8 at least. So as long as we get there, then we're pretty good. So in this second scenario here, 0.2 and 0.8, all three components kind of match that. I just look for a scenario that separates them the most after that point. And it looks like that can be done with an RP8 or an RP18. Either one of those I don't really see big changes with. If I look at the first graph and I do the 0.2 to the 0.8, well, this kind of setup is not going to be very good either for a silica plate because these two are too low. So it looks like the RP2 right here, 0.2 to 0.8, that's a pretty good kind of scenario to go with. These three, they're a little bit higher up, and I would have to wait a little bit longer for these to develop. So that's why this RP2 is probably going to be the best one out of the choices that I would pick to develop my sample on. They're separated far enough. The separation does not increase by going to RP8 or RP18. And I don't have to wait forever because they're kind of in the middle of the retention factors, 0.2 to 0.8, and these are smack dab in the middle of those. All right? Okay, some other things that I need to talk about as far as the TLC plate goes. We can calculate efficiency of the spots, which is basically the efficiency of the plate. How good is it for separating? And we do that by doing an equation similar to chromatography. N is the efficiency here, is equal to x squared over w squared. The x is how far the spot traveled, and the w is how wide the spot is, the diameter of the spot. So if you're looking at comparing different spots to each other, then you take how long did it travel and how wide is the spot, and you can calculate what we call efficiency. How good was that spot basically for the plate? If you have a really wide spot, that means it's a smeary spot, right? And that's a large number. And if you put a very large number here on the bottom, that efficiency is going to go very low. If you have a spot that's moved the same distance, but it's a very tiny spot, which is what it should be, it should not be a smear, then that means that this width is going to be a very small number. And the smaller the denominator, the larger that number is going to get. We can also calculate the theoretical plate for a TLC plate. And that's H, just like it was before, is equal to X over N. So N is the basically efficiency from the first equation, and the X is going to be how far did the spot travel. So how far did the spot travel divided by the efficiency for that spot, and that will give me the theoretical plate height. Something else that we can also do with the TLC plate is resolution. And when it concerns resolution, we're looking at are two spots separated enough, yes or no. This resolution is very similar to the chromatography equation as well. We see the big 2 out in front, and then the x's are basically the distance of the spots subtracted from each other. And then we'll divide that by the width of the spot that's added together. This way we'll know if two spots are really close together and those widths are very large, then we know that the resolution's not going to be very good. So we typically kind of keep the same resolution number that we did in chromatography. We're looking at 1.5 or greater, and if so, we're pretty much good to go, and we can say that those have separated quite a bit. Here's another slide that I would like to show you before this video ends, and this is a TLC plate, and this is a TLC plate of those steroids, testosterone, hormones really, hydrocortisone. And those three compounds have separated on a TLC plate. And this is just related to how it goes to chromatography when we get to that point. So if you look on the TLC plate, spot number 1 has moved up the slowest. It's not really moved up that far at all, right? And because of that, if we want these spots to run off the plate, well, I can kind of change this up. So if we said that this plate was a column, how long would it take for it to come off the column? Well, number 3 looks like it would come off the column first, or the plate first. Well, in chromatography, that means this very first peak that I would see in a chromatogram would be that particular component. The one that's the middle one, well, it's going to eventually come off, but it comes off second. And that's what I see in the chromatogram over here. And then finally, spot number 1, that looks like it's going to take the longest to go up the plate, which means it's going to take the longest to come out of the column if this was a column. And that means that in the chromatogram on a normal chromatograph, that spot number 1 would be the last peak that would come off in a chromatograph instrument. All right, so that's how TLC relates to the field of chromatography when we get to that point and talk about GC and IC and HPLC. Okay? All right, so some other things, problems. What kind of problems do I really see in TLC? You get very many problems. It's not very user-friendly. They're easy to run, but the problem is that there's so many things that can happen that can go wrong. One, the compound is streaked. Well, that means that you've got too much sample that's loaded there. You need to dilute the sample and you need to re-inject that sample onto the plate. Another thing, if it's streaked, that could mean that your sample is too complex. You've got multiple components on the inside, and those components need to separate off, and you're just not giving it enough time to do so. You need to choose bigger plates, different mobile phases, different stationary phases, you name it, you probably need to change something. The next, what if the solvent line is crooked? This is that mobile phase line that shows up on the top of the TLC plate. If the solvent line is crooked, then that means that your absorbent has probably flaked off throughout the plate. Or you've touched the plate, and because you've touched the plate, that stationary phase is now damaged. Another reason that your solvent line can go crooked is because maybe your plate is touching the side of the TLC chamber or the beaker or container that you're putting your plate into. So sometimes that can actually make the flakes come off. That can actually attract some of the mobile phase to it, believe it or not, and we can get a crooked solvent line because of that. Too many random spots. Well, this is your prep technique. So did you prep your TLC plates the right way? Yes or no? And if you were very sloppy with your prep technique, then you will see drips and splatters of your sample all over the TLC plate. And you don't want that to happen. So because of that reason, I tend to tell people to make sure that they go up from the bottom to spot the plate. Never take your capillary tube, or if you're using a micropipette, to basically go over top of the plate and down and then spot the sample. Go up from the bottom. And if you don't see any spots at all, you probably didn't place enough sample onto the plate. It might not show up with the indicator that you're using, so you probably need to choose a different indicator. And did you make sure that your solvent line or your mobile phase at the starting point, was it above the mobile phase layer? If not, your sample probably soaked into the well down below instead of getting pushed up through the plate by the mobile phase itself. Here are some troubleshooting aspects that basically we've talked about already, and this is just what we confirmed on the previous slide. So if you want to take a pause of the video and just kind of read through some of this stuff, it will tell you some of the common problems and how to fix them, but it's basically things that we've talked about already, so I'm not going to go into that much detail with it. So this concludes our speech on TLC. Very simplistic technique, a very simple technique that we do for prep work, though. We don't really do quantitative work with it at all. So in organic chemistry, you probably will do some TLC slides. You will do some TLC slides with us as well, just because we introduce the concept and we talk about it in chromatography. But, you know, other than one lab, you're basically not going to do any more TLC work with us at all. It's just really that. Just because it's not a very common technique that goes forward in a chromatography lab anymore. So good luck with the assignments. Good luck with the TLC test. Good luck with the remaining videos, if there's more than this, but there probably is not. This is where it ends. Bye-bye.